Okay, in this example we're going to look at what seems like a fairly simple situation, but begin to see how complex it really begins to be. That is, we got a fixed end at the left, a roller at the right, constant EI along the length, and we just have an end couple applied, this M naught. Now, it might seem highly theoretical, and I suppose it really is, but it turns out that this scenario is one of three basic core problems, or core aspects, that is, of all of the computer-based structural models for beams. Right? And so this is really 1/3 of what's really going on inside computer models, plus a whole bunch of stuff that is associated with the loads that are inside the beam. Right, so we'll get into more of that in just a second, but let's see how we're going to approach this. Right? And of course the first thing we really should do is statical classification. Count up that we've got 3 reaction components at A, we've got 1 at B, that's a total of 4. We only have 3 equations of equilibrium because there's no special conditions or anything that we also have to satisfy, so only n equals 3. So it's statically indeterminate to the first degree, 1 redundant reaction. So we'll select one. I select BY, leaves us a stable structure, and we end up with then a cantilever beam with this end moment applied, with a little deflected shape where the deflection, transverse deflection at the end, we look up in a table that's minus m naught L squared over 2EI. If we don't find it, then we have to go, of course, and derive this value. Because the problem statement asks us something about the rotation at B, that's why I've got the expression written here for the slope at B. Right? So, anyways, take the time to go verify in the table that you can find that expression, and then our next step is to put this back into place, right? Because this is deflected down at the tip, and we violated the condition that at that roller there's supposed to be no displacement at all, right? So we're going to put that back into place with this unknown value for BY. The model that we're going to use there will tell us that that deflection that happens out there is BY L cubed over 3EI. Again, here's that expression for the rotation in terms of the unknown value of BY. Right? Compatibility is how we put this all back together. Right? That when we superpose the results of these two, that's going to give us the total here. Right? The sign is already embedded in each of these. Right? And when we do that, well, they're supposed to equal 0. And so when we put that in there, we can solve for BY in terms of the applied force, m naught over L. Right? Now notice, that's a moment. It has units of force length over a length, so we're back to units of force, so that works out about right. The positive sign tells us that we guessed, in a sense, the right direction. Everything is consistent, so it's acting upwards here. Okay, and so now we can go find the other reactions just through basic equilibrium. Right? We draw the member. We've got the M0. We found BY already. That leaves us with only the AY over here and MA. Of course, AX is trivial. It's 0 here, and I haven't even bothered to show the axial reaction here. By sum of forces in the Y, AY has to be equal opposite to what BY is. And then note that when we take those two, it's a force couple, and multiply by L, we'll get 3/2 MO, but we got MO going the other way, so there's a leftover 1/2 of MO going in a counterclockwise fashion. That's why MA actually has to be not only half of MO, but it has to be in the same direction to equilibrate all this stuff. Right? And that gives us all the equilibrium. Now that's not everything we've been asked to find. We're going to do the rest in another video. Right? So we only found the reactions here. That's the first step. We need the shear moment diagrams, the equation for the elastic deflected shape, the final equation for the rotation at B, and we actually already have the qualitative consistent deflected shape, but why is it going to look like that? Well, that will come, of course, from the composite moment diagram when we're done. That's what we'll do in some companion videos along the way.